Well, let's look at the messy details of calculating the angle between V and R. Clearly, the derivatives are these. And I think everybody agrees, so it looks like maybe I got lucky and did it right. Okay, so the angle is going to be the inverse cosine of V dot R over magnitude of V times magnitude of R. But, you know, that's what you do with the dot product. And if you're not real familiar with that, you've seen it and it'll become natural. Okay. Oh, well, that's the inverse cosine of what? Well, V dot R, you're going to have an omega times -4 times the sine, and a 4 times the cosine, which is going to give you -16 omega times the cosine, right? And again, I've just written parentheses because the argument is always omega t. And you can fill those in if you need it. And of course, in your final expression, you probably want to fill them in, right? But just for demonstration, there it is. You can fill in the details. And then you divide by the product of the magnitudes, right? Okay, well, the magnitude of R is the square of 4 times the cosine of omega t plus the square of 9 times the sine of omega t, right? So that's just 16 cosine squared of omega t plus 81 sine squared of omega t. Very straightforward, right?
Where do you get that denominator from?
Magnitude of V times magnitude of R. Now I just put them all under one square root sign because I went and wrote a big square root sign, didn't want to erase it, okay? So right there is the expression for the magnitude of V, right? I mean, it's the square of this plus the square of this. Okay, look at the video and ponder it if you need to. But it's very straightforward. If I ask you to write it out, that's what you would write out. And what's the square of V? Well, you got -4 omega times the sine and 9 omega times the cosine, right? Well, you square that, you're going to get 16 omega squared times the cosine and 81 omega squared times the sine, right? Now, if you want to, we can do this. We're going to get a little crowded in here, but now it's the product of 2 square roots. Now you see certainly that this is magnitude of V, this is a magnitude of R, but I could combine them in 1 square root sign. You know the algebra. Okay? It's not a problem. Okay, well, there it is, and it's clearly not always 0. Now, if we had 4 and 4 here, it would be 0 because we wouldn't have to worry about this messy denominator, right? Because we'd have a -16 here and a +16 here. Okay? But that's not the case. So we got some angle between V and R. Okay? And it's not 90 degrees. And clearly from the picture, it was obvious, I think, that it wasn't 90 degrees. If you draw an ellipse inside of a rectangle, in tangent at these points, it looks something like this. This is your origin and this is your R vector. Your V vector is here. Okay? Now the closer you are to these points, the closer this angle is going to be to 90 degrees because the ellipse is tangent to the rectangle. Okay? But as you get further away, if we move, let's say, to here, that angle's not 90 degrees, less than 90 degrees. Okay? And you can draw an exaggerated ellipse and convince yourself of that, and I'd recommend it. Okay? So, V's not perpendicular to R, which means since A appears to be parallel to R, that A isn't parallel to V either, or perpendicular to V. Okay? So I can say that, okay, right? A is not perpendicular to B. Okay? So now we have an acceleration. Okay, here's our acceleration vector. And here's our velocity vector. And here is a right angle with the acceleration vector, right? And I don't want to do that. I want to do a right angle with the velocity vector. I can do it either way. Okay? So, sorry, we have a vector parallel to the velocity vector, right? And then we have the direction perpendicular to the velocity vector. Okay, so this is direction parallel to V, which is also tangent to the path, right? And here's a direction perpendicular to V. We call this the normal direction, and that's a terminology that you'll be getting used to both here and in physics, okay? The direction perpendicular to this one, okay? And we see the acceleration vector has a component in the direction of V and a component in the direction of the normal vector, right? Okay? And this is extraordinarily important because what this tells us basically is that this particle moving around this ellipse carries a coordinate system with it. And the coordinate system keeps changing direction as the direction of the velocity keeps changing. Okay? Within that coordinate system, we can talk about the components of the acceleration vector. And the reason we want to do that is because the component of the acceleration vector in the direction of the velocity changes the speed. Speeds the particle up or slows it down. The direction perpendicular to that changes the direction, results in the curvature. That's a lot to digest. You probably have indigestion right about now.
So that means that the speed is not constant?
Can't be. Think about it. Okay? Like if this takes 6 seconds, then this takes 3/2 a second, 3/4 of a second. Where is this thing after 3/4 of a second? It's not at 45 degrees, which means it takes longer to do one 45 degrees than another, or equal times to do two different angles, right?
We're also moving at different velocities at different points to get different measurements, because we have to move faster upwards when we're going up.
Exactly, and that gets into the definition of the radian and stuff that we'll be looking at in physics tomorrow. Okay? So yeah, if you're, well, that's a little complicated. I'm not going to talk about it right now, but your intuition is exactly right. Okay? I mean, you might have gotten something backwards there, might not. I don't even know because I didn't quite hear everything you said.
I was just saying that.
I don't want to hear it. Okay? I don't need to hear it. It was either right or 90 or 180 degrees wrong, and if it's 180 degrees wrong, all you got to do is reverse it. Okay? So, but it was the right insight, just the right intuition, very good. Okay? And many things are like that. It's really easy to get it backwards. But you've got the idea, and then you think a little more clearly. I kind of think it was right, but I didn't hear all the words. Okay, so what we have here now is what we call a parallel and a perpendicular. Okay? And all we have to do to get these vectors, well, we've got our V vector, right? And we got our A vector, right there they are, smiling at us. Okay? Now for different paths and different parameterizations, it might differ. Okay? But we've got them, so all we have to do is project this vector on this one. Okay? Project A on V, then project A on a vector perpendicular to V. Now I might write down projections, because it's been a while since you saw one, like, you know, linear algebra last fall, right? Probably haven't seen a projection since then, but maybe.
We saw some last spring.
Yeah, you saw them in statics. Yeah, so you know about projections. Projection's a very simple operation. I mean, it gets messy with these vectors, but it's easy enough to write it down. It's hard to keep track of everything and write everything down right and not make a mistake, but it's an easy process. And it's an easy concept if you really understand the concept instead of using an engineering formula. Okay? That's what we taught you the concept in linear algebra. You get to engineering and you forget it. Now, there's good reason for that. I'm not knocking engineers. There's a difference in orientation. Okay? Engineers use, mathematicians prove, and mathematicians understand kind of a smaller realm, but in more abstract terms. And you don't want mathematicians building your bridges and designing systems, critical systems, okay? You might want them to back up the engineers, okay? Make sure the engineers are doing the math right. But engineers kind of know how to do that anyway with software programs.
Or January.
So, there's an interplay between engineering and mathematics. I want you to understand the principles so you don't have to carry too much crap around to do your engineering. Principle of simple picture for projection. And then just use your dot products and stuff.